want to just pick up straight where we left off, and we have been talking about the linear transport equation. Which looks like a time derivative of u xt was the concentration or mass density at the point x at the time t, and v is the velocity vector. We're dealing mostly with incompressible fluids, in the case where you have divergence of v equals 0. And I'll give you a quick example now for a particular velocity function v. So let me show you what we're going to set up. So let's take a domain omega, a region in R2. So here, omega is like an infinite strip or an infinitely long tube. Instead of an artery with boundaries, we'll take, for the purposes of this contrived example, like an infinitely long strip with fluid flowing through it according to the following equation for velocity. So here's the velocity vector. So here we're working in R2, like before, using vector x hat to represent coordinates x, y. And here's a velocity vector. So at each point, you're traveling at each point, x, y, your velocity travels in this direction. And two things I'll note about this. You can quickly verify that the divergence of v is equal to 0, and that v restricted to the boundary is also equal to 0. The boundary, of course, being the line determined by y equals -1, and the line, horizontal line, determined by y equals +1. Okay, and so remember then the definition of characteristic. And for your first in-class exercise, so we'll do some participation with this. I'll ask you to please calculate the characteristic with initial condition. With the following initial condition, taking t naught equals 0, and then taking x naught equal just arbitrary points a, b. So please find a formula for that characteristic. I'll give you a minute to look. So having given you at least some time, give you that feeling of working in the exam situation, I'll now explain. So this is a system of two ODE for X and Y, and you could write it like this. So this is from ODE class or even from linear algebra class, using Isaac Newton's notation that the time derivative is represented by a dot. I get the derivative dx dt should be a. If this derivative is now equal to what? So velocity function with just x of t and y of t plugged in. So this is now 1 minus y of t squared and 0. So you have this system of two differential equations that you want to solve. And in this case, it's quite simple because y prime equals 0 gives you y is equal to a constant, and therefore y is equal to b due to the initial condition. And you now solve x dot or dx dt equals 1 minus b squared, which is again just a constant. So you put it together. And those are your, oops. So integrated constant, you get t times that constant plus another constant. And according to the initial condition, that must be a. So now you've got this formula for the characteristic line that goes through A, B. And it is a line, a linear function in this case. Any questions on that derivation? So let us solve this equation with this determination of velocity, but we also need an initial condition. So let us take u of x at time 0 to be some prescribed function g of x. And so let us solve this with method of characteristics. So what you get, in general, what you get is this equation, remember, that you take this Lagrangian derivative which is the time derivative of u, but with the characteristic plugged in. And that's equal to W twiddle, which is equal to your W term, but with x of t plugged in. And in this case, that term is equal to 0 because the divergence of v is equal to 0. So this is u sub t plus gradient of u dot v plus w equals 0 with w equal to 0. And so you get that this derivative is equal to 0. In other words, you get that this function is equal to a constant. which constant? Plug in t equals 0. Plug in t equals 0, you get u of 0a. U of 0a is g of a. Third question? So if I plug in 0, I get u of 0a. So this is constant, doesn't change in t. So just plug in 0, and that's equal to g of a. Okay, so this is u with right. So the question was, for the audience, the question was to explain again why this is true, and maybe go over what did this mean? That's u of t x of t. Okay. And now you do this trick where you have this equation. I'll just write it down again. And I think you would like to re-express this in a way that no longer references the initial values a, b. And if you can do that, then you've got a solution that started along a characteristic, but now no longer references those initial conditions, and therefore a solution that holds for every x and every t. So you kind of want to look back now at these two equations. And so in particular, you can solve this equation for A and plug that into G of A. So let us do that. So what do we get? A is x minus t plus tb squared. And this is now equal to u of t x. And if you're following along in the book, so this is where the book stops, but but no, you've got b squared here, so you're still referencing your initial condition, but that's no big deal because b is equal to 1. So if you vary b around, that's the same as varying 1. And so here now finally is your solution. We'll get the computer out of the way there. Okay. So for any t, for any x, u has to have the form g of x minus t plus t y squared. So it's kind of nice. You solve it on a characteristic, but if you can then solve for x and y in terms of those initial conditions, a and b, kind of inverting that system of equations over there, that'll then give you a general formula for xt. So this is an example of solving transport equation with method of characteristics. Question?
So now x is other.
So my x hat is coordinates xy, and this this x and this y are coordinates, and this x is a vector because you know takes into 2 components. So u is a function of three variables, t, x, and y. G is a function of one variable for the initial condition, and you're plugging into one variable function an expression that involves t, x, and y, but it's still a scalar number. So it all works. Okay. And that question was, for the recording, that question was to clarify when x is a scalar and when it isn't. So I maybe should be a little bit more careful of keeping the hats. Okay, I've got another application of method of characteristics, and in fact, you can use it to solve the wave equation. But before we do that, I need to actually, well, I don't really need to do this, but it's just kind of interesting. I'll derive for you, I'll show you how to derive the wave equation. And so I'm no physicist, I don't claim to be, but I do think it's worth seeing these derivations. And there's a number of them floating around. Most commonly, what you try to do in this model with like the vibrating string is that you will partition the string into small pieces and apply F equals mass times acceleration on each little piece. And if you make the partition small enough, as the mesh goes to zero, you can sort of treat each piece like a particle and do a model that way. That is in one of your textbooks. I'll do a presentation from the other one, from the applied PDE, which actually allows us to do F equals ma, but on the total momentum. So directly on the integral and differentiate under the integral sign. It's a really clean way to derive this equation. I really like it, so I want to show it to you. But let's start from the beginning. And one reason for deriving these equations, I think, is to even show you the extraordinary number of assumptions that you have to make to get these simple forms. So even if you want to look at a toy model of the vibrating string with no assumptions, you get, you get something that's very complicated and maybe even intractable. And so as a physicist, you would ask yourself, like, what are the contributions that really matter? And over time, you develop these assumptions. And so I'm not going to get into whether or not this assumption is good or bad or whatever. I'll sort of state the assumptions and then use them to create a model that you will understand. Models of very specific kind of small instance. So the setup. You take a vibrating string of length L. And you can imagine yourself plucking the string. And so maybe it's at rest at time equals 0, and then at a later time I pluck the string and it starts vibrating. And so I've drawn sort of a little picture of what a vibration might look like. And so in this case, uxt in this case, uxt is equal to the vertical displacement of the string. So we're not considering a situation in which there is horizontal motion of this string. That could happen, but we're just not considering that situation. We're considering the vertical motion only in this example. As before, I'll use rho to represent the mass density. And as before, rho has units of mass over length. I need to introduce a new quantity, in this case, tension. So my quantity, capital T, is going to represent the magnitude of the tension vector at any point. So at any point here at a particular time, you're going to have tension pointing in a certain direction, and the magnitude of that tension, that scalar value, is what I'm calling TXT. Magnitude of the tension vector. And assumptions. First, that the displacement is small. So think of plucking a violin string or a guitar string, you're not moving very much. That's right. Relative to the length of the string, the displacement is small. Second, as I've already just stated, only motion in the vertical direction. And three, I'm going to ask that the tension force is in the direction of the tangent line. So tangent line of what? So uxt is the displacement. So yeah, tangent line to what's drawn there. And so what is the equation? It's like x equals x, y equals u of x, right? So the displacement u is like the y value, and then you're taking the graph of u. So the tension force goes along the tangent to the graph of u. And with these assumptions, we can go to work. And so this T has units of force, so that's like kilograms times meters per second squared. And let's see, let's make up some notation. So at any point, you can, let's say this is like, maybe take this left endpoint as 0, 0 on the plane. And at any point, you can look at the horizontal part and the vertical part of the tangent line. And the angle theta made with the tangent vector and the horizontal, we'll call that theta, and that's going to depend on x, on where you are. You know, x is on the x-axis, and this is like the x-axis, and this is the u-axis. But it'll also depend on what time you're at, right? Because as the time progresses, this string will continue vibrating and bending, and then you'll have different angles at each point. And I'll note actually, I'll make this a class exercise, so take 30 seconds. can you relate the tangent of theta xt back to the function u? What term goes on the right-hand side of that equation that involves u? Okay, Kevin, given you a few minutes to think at least. I'll redraw the picture to make it a little bit bigger. So look at this section. So you know that tangent theta, of course, is opposite over adjacent, and that's what? The change in u over the change in x, except you're doing it infinitesimally. So this is partial with respect to x of u. So the change in u over change in x, and then taking a limit to get theta, give you this. And I mean, you can think about this as maybe you could say, like, because tangent is continuous, like it has to be, like maybe if you didn't want to work on the level of tangent line, you could take these rise over run approximations for the curve and let them go to 0. And in the limit, you'd get the derivative, and in the limit, you'd get tangent. Or I just kind of like, you know, you're already at the derivative level or the infinitesimal level. That slope of the tangent line is, of course, the derivative of the function. That's what we learned in calculus. Okay. And I'm going to derive this equation using two principles, F equals ma, but also the conservation of mass. So what is mass conservation going to say in this context? So let's consider a small interval inside this line. Maybe going from A to B. And that's at t equals 0. And now at t equals t naught, what happens to this portion of the string you've now got? Something like that, where this section of string is now bent. In that kind of direction, and you'll notice that these lengths are not the same. Right, and correspondingly, the density will then change. You know, if you stretch out the string to a higher length, the density will correspondingly decrease, and you're not necessarily going to be able to keep track of that at every single point. But what you can say is that the mass in this interval is the same as the mass in that interval. So even though the length of the density may be changing, the mass will not. And so let's write down the mass that's included in this interval from A to B. Yeah, right. So that total mass from calculus 2, we should integrate the density function at time 0 dx. Because the high school physics says density times length to give us mass, but then when density varies, it turns into. And so what about the other one? You really need to do the same thing, but now you must take a line integral from this point to that one. And how do you do a line integral? You still integrate from A to B. Well, this time rho of xt, but now you include the element of arc length. And since the graph was like x, u of x, the element of arc length, square root of derivative of x squared plus square root of derivative of u x squared. The element of arc length in this particular situation becomes square root of 1 plus partial with respect to u. So you get this nice equation.
Can you show that? How you got that?
So yeah, the question is, can I explain that a little bit more? So explain how I got this for element of arc length? Yeah. So the graph there is t goes to x of t u of x of t. But actually, I shouldn't even use t because there t is time, but here it's just a parameter. I should just say the graph is x u of x, right? Any fixed time t is the graph. And so you want to calculate this arc length period. What you're doing, you just take the derivative of this, which is 1 du dx. And when you're calculating arc length, when you're deriving this in Calc 2, what you first do is sort of like partition it into line segments and take a limit. And what you end up doing is integrating over basically the length of the tangent lines at each point. So take such a tangent line, and then you're just asking, like, what is this length? And basically, you go over 1 unit, and you go up UX units. And then by Pythagorean theorem, you do it. And so the next principle is force equals mass times acceleration, but appropriately interpreted. Right? And so I want to break this up into horizontal and vertical components. And here I'll actually use the assumption that there's no horizontal motion. So if I look at the total force on the string at any particular time t in the horizontal direction, that's going to be force that's coming from the right endpoint, minus force that's coming from the left endpoint. So tension in this case, tension at a point is interpreted to be you're pulling on the rest of the stuff that's behind you, right? So here, this is tension at this point is the rest of the string pulling this part of the string in the direction of the tangent vector. And so if I want the total horizontal tension, I want the horizontal component of, or like the horizontal, of the magnitude of the horizontal component of tension applied here, minus the magnitude of the horizontal component of the tension applied here. So think of the string at rest. This is a tense string. There is tension there. And you've got some, you're like holding it in place, so they're holding the string. So you've got some tension applied at the right endpoint. And I think of that tension as sort of percolating all the way down and then giving me some tension on the left endpoint too. In order for this spring to be at rest, I'm not saying that there's no tension there, that there's no force, but I am saying that the difference between the force here and force there should be 0. Because the amount of force you put here should be equal to the amount of force there. If it's lost, then there's probably some motion horizontally accounting for the loss. Like if I instantaneously let go of the spring, of the string, all of a sudden there's no force here, but there's still force there. And then what you see is this horizontal motion. There's even these high-speed videos, right, where the person's holding a spring, and there's like, so there's sort of holding a spring at rest. So you've got force at that end and force at this end, but they balance. And the person lets it go. And in super slow motion, you can actually see that the spring at that end stays stationary, and the spring slowly collapses from top to bottom as the motion sort of accounts for all the force. It's kind of neat. If you don't know what I'm talking about, I can maybe post the video. But right, so the horizontal part, that's tension times cosine theta, so that's going to say that the difference is equal to 0, so the right hand and left hand horizontal components have to be the same. And in fact, this has to be true for any A and any B, not just endpoints, because there's no horizontal motion anywhere. So the forces have to balance all the time, and that implies taking A equals constant and B equals X, that implies that this function must be constant. I mean, it can change with respect to t, but not with respect to x. This is at a fixed particular time t. And so we'll call that constant tau. And tau can depend on t. So this F equals NA plus horizontal, no horizontal motion is implying to us that this quantity is constant in x, and we'll call it tau. Now, on the other hand, what about the vertical component? Let's do F equals mass times acceleration, but let's write this as derivative of momentum. Derivative of momentum. Momentum is mass times velocity. And here, let us talk about the vertical component only. So in this case, we get I'm going to need more space. We get this difference in vertical components. At the endpoints A and B, is the net force or total force applied to the section of the string from A to B. And on the other hand, what is the total momentum? So since mass and velocity aren't constants, we can't just take two quantities and multiply them together. We need an integral. So I want to take the derivative of the total momentum. So I should integrate from A to B, and I'm interested in density. So instantaneous mass, if you like, is density times instantaneous velocity. So you multiply them together at the infinitesimal level and then integrate. That's, in some sense, that's the point of calculus too, is that these physics laws from high school, that's just two quantities multiplied together. If you look at them infinitesimally, you can still multiply them together, but then you integrate to get the corresponding formula.
Why is it use of X?
So this is that's the direction that the force is in. The position, derivative positions. Also.
Yeah. Okay.
This is respect to fixed time t. Right. And then you need to integrate this with respect to arc length because you're integrating like a section at a particular time t that won't be a straight line. Okay, so this has to somehow turn into the wave equation. And the first step is, you could just go straight ahead and take this derivative and start working, but I think it's much more civil to use this mass conservation. So I can now represent this total momentum as what? Rho xt becomes rho x0. So this just becomes rho x0 times partial with respect to x dx. And you might say, wait a minute, like these two integrals are equal, but how did you substitute this part of the integrand for that part of it? And the reason is, this argument we've done a couple of times now, if you take this to the other side and bring it under one side, one integral side, rho x0 minus rho xt squared 1 plus 2x squared, since this integral is equal to 0 for every a b, no matter which one you pick, as long as b is greater than a, you can once again conclude that on the level of the integrands, these two things are actually the same. So that's an argument we've seen with deriving a different equation, and it's actually this that I'm using to justify this step. And now we'll take the derivative. And now I'll take your point, William. I think you're right. I completely screwed up. So it should be in the time direction.
That makes a little more sense.
Should be in the time direction. Velocity with respect to time
I was confused.
you're moving in a vertical fashion, and so clearly your velocity is distance over time. Excuse me.
I was also a little confused because we're looking at force in the vertical direction. I didn't really get why we were incorporating the vector that is not vertical.
Yeah, right. So I apologize for the mistake. Thank you for the correction. Well, let's now bring this derivative into the integral side. So I get integral from a to b, rho x0, UTT. So we're getting there. Got a second derivative of u. And now I have to work on this far left-hand side. So this argument is actually a little bit clever. What I'm going to do to relate this back is I'll multiply and divide by cosine. So you see what I've done? I've multiplied and divided by cosine dt here. And I want to make two observations simultaneously. And the first observation is that these two quantities are one and the same. Because, one of our assumptions from no horizontal motion was that tension at any point in times cosine was equal to this function tau t. So they had to balance. So since these two things are the same and they're both equal to tau t, I'll just factor that out. And times what? So tangent theta of b of t. But we also noticed that this was equal to ux minus tangent theta of a of t. So tangent theta a of t. Writing so quickly, kind of missing the theta there in the last part. So tangent theta of a of t is u sub x. Using those steps, we're basically done because now I can apply fundamental theorem of calculus and say this is the integral from a to b of the derivative of u sub x. And this is now equal to that far right-hand side, or we'll rewrite it. Yeah, and now you can fill in the gaps. We're basically done. So we'll use this argument. So bring this inside the integrand. That's fine. It's a function of t. Treat it like a constant. And then bring this to the other side. Make it a single integral from a to b. Single integral from a to b of tau times uxx minus rho times utt. So therefore, the integrand has to be 0. Suppressing the variables on uxx and utt. And now it's common to make the assumption, this is not a consequence of anything, it's common to make the assumption that tau is constant. And therefore just call it tau instead of tau of t. That's an assumption, it's not a consequence of anything. And so now what you would do, well, this model is a model that describes the situation when tau is equal to constant. And it's quite reasonable. That's like saying like the tension on your guitar string sort of isn't changing while it's being plucked. So it's a reasonable assumption. And now what you can,
It's hard to have a training for it.
well, you could look up, whether that's physically reasonable, and you could write down the equation and you could try to solve it. So I welcome you to do that. And now, so dividing both sides by the density. The question, by the way, for the audience was like, what if this isn't constant? What could you do? And the answer is you would just have a different model modeling a different situation. So this is going to be rho over tau, uxx. And so this, density and tension, they're both positive quantities. This was a magnitude. So it's common to write this as c squared, or c squared equals rho over tau.
Wouldn't it be tau over rho?
Yeah.
Tau over rho, excuse me. Okay, and so force, so check this too to make sure everything's right. So, but force over density should have units of meters per second squared. And therefore, we're out of time, so I won't do it for you, but therefore, the units of C are now like meters per second. So C is a velocity, it's called the propagation speeds or the wave speed. So remembering this has units of like mass times meters per second squared, and then you're dividing by something with units of mass over length. So that gives you the extra copy of meters on top. So you get meters squared over second squared in kilograms. Okay. And that's it. So that's how you go from those assumptions to this wave equation and with this constant. And it also discovers for you the physical interpretation of that constant tau over rho. And so to probe into your question a little bit more, you're describing a situation where the speed is variable. That could certainly happen. PDE can solve those equations. It's just that in the classical wave equation, you assume that the speed is constant. Yeah, that's interesting. So the question was like, how does it change sound when you're changing this constant? Of course, this is not a model for sound; it's a model for vibration. They're very closely related, not exactly the same. We'll talk about acoustics another time. So thank you for your time and attention. And tomorrow, I think we'll just dive right in and solve it and derive the so-called Thalen-Berg solution. Tomorrow, in the sense of the next class period. Yeah, Wednesday. That's right. Thank you. And so it's a quite nice solution, and you can do it with the method of characteristics. So we'll see you then. Thank you, everyone. Take care.